Hey folks, welcome to the second video of 3.4. This one's about work done by conservative forces versus non-conservative forces. Specifically, we'll talk about work done by non-conservative forces, and I'll remind you of what we do with conservative forces. So we start with our little, I guess you can call it a definition. Work done by non-conservative forces is equal to a system's change in mechanical energy. So we just talked about in the last video that if a conservative force does work, we have no change in mechanical energy. But if a non-conservative force does work, that there is a change in mechanical energy. Since work is defined as the change in energy or the energy transferred by a force, the work done by a non-conservative force must be equal to the system's change in mechanical energy. Now, there's like two ways that this can flow. You can either have non-mechanical energy becoming mechanical energy. And so, my son just got like a remote controlled car for Christmas. And so that remote control car has a battery in it. And that battery powers the motor in the car. And the motor moves the car. So the chemical energy inside the battery is transformed into mechanical energy to move the motor, and that's transformed into the mechanical energy of the wheels turning in the car and moving the car. And then it also goes the other way. So sometimes you can take mechanical energy and turn it into non-mechanical energy. And so the big thing that I think about is like wind turbines or wind farms. So a wind turbine can generate electricity. And so if you take more physics, maybe in high school, you'll learn about how a generator works. Basically, the wind turbine, the wind pushes on the blades of the turbine, and so the turbine spins. That's mechanical energy because that's energy of motion, and it spins something inside the center of the wind turbine, and that generator takes the mechanical energy and turns it into electrical energy. Anyway, what you need to know is how to work with this idea. And so put into an equation, the net work done by a non-conservative force is equal to the change in mechanical energy of a system. Now, there are multiple ways that you'll be asked to work with this, and so there are multiple ways that you can work with this in an equation. This is by far the most general, that the amount of work done by a non-conservative force, non-conservative net force, is equal to the change in mechanical energy. It is important to remember that change in something is final minus initial. So that is another way that you can work with this mathematically. If you find the difference in energy, final minus initial, that will tell you how much work is done by the non-conservative forces. I like to add the initial energy to both sides, and I like to think of this equation this way. So if I am left to calculate something, I am going to use the definition of work in specifically this way. The reason I like this is because it tells a story from left to right in chronological order. At the beginning of some event, there is some amount of mechanical energy. During the event, some amount of work might be done by non-conservative forces. And when all is said and done, we reach the end of the event and we have a new value for mechanical energy. So this is how I like to use it. The other reason I like it is if that work done by non-conservative forces is zero, then we are back to our conservation of energy concept, that the amount of mechanical energy is constant throughout some amount of change. So this form of this equation, I think, is versatile for setting up calculations, whereas I think like this equation up here is the best for thinking about things conceptually. And so you'll see all sorts of looks at this, but that's the general concept, is like non-conservative forces can do work, and that work is equal to the change in mechanical energy of a system.